How do you calculate Rankine cycle reheat efficiently? Imagine a steam power plant trying to squeeze out every bit of efficiency from its cycle. Reheat technology is like giving the cycle a boost, but how do engineers figure out just how effective it is? That's what we're here to uncover. First, picture the cycle. Water starts as a liquid at the condenser, then gets pumped to high pressure. It's heated in the boiler to become superheated steam, then expands in a high-pressure turbine. After some work is done, the steam is reheated at constant pressure, then expanded again in a low-pressure turbine. This process is called reheat, and it helps improve efficiency by raising the average heat addition temperature. To calculate how well this cycle works, you need to know the states of the steam at key points. These are the points where the water or steam changes pressure, temperature, or phase. For example, state 1 is the saturated liquid leaving the condenser. State 2 is the compressed liquid after the pump. State 3 is the superheated steam entering the high-pressure turbine. State 4 is after the steam expands in the high-pressure turbine. State 5 is after reheating, and State 6 is after the low-pressure turbine before it condenses again. Next, you find the properties at each of these states. Using steam tables or thermodynamic software, you get the pressure, temperature, enthalpy, and entropy. Enthalpy tells you how much energy the steam has, which is key for calculating work and heat transfer. For example, during expansion in the turbines, the entropy stays constant if the process is ideal and isentropic. Now you can calculate the work done by the turbines. For each expansion, subtract the enthalpy at the outlet from the inlet. Add these together to get the total turbine work. Then, find the work needed to run the pump, which is the enthalpy difference between the liquid states before and after compression. The heat input is the sum of heat added in the boiler and the reheater, which is the enthalpy difference between the water leaving the pump and the superheated steam entering the turbines. Finally, you find the efficiency by dividing the net work output, turbine work minus pump work, by the total heat added. This ratio tells you how effectively the cycle converts heat into useful work. To get the most out of reheat, engineers carefully choose the reheating pressure. It's usually set between the high and low pressures to keep moisture content low and blades safe. Practically, you assume ideal processes for turbines and pumps to simplify calculations. Multiple reheats can boost efficiency even more, but they add complexity. Reheat cycles generally improve efficiency by about 4 to 5% compared to basic Rankine cycles. So, to sum up, calculating the efficiency of a reheat Rankine cycle involves finding the properties at key points, calculating work and heat transfer, and then applying the efficiency formula. Adjusting the reheating pressure helps optimize performance, balancing efficiency gains with turbine blade safety. This step-by-step approach makes understanding thermodynamic cycles much clearer and shows how engineers improve power plant performance.